let's start. So, since I received a huge number of emails from you, probably will be short of the tutorial, or we just dedicated to questions regarding the second part of the lectures. Before moving on, I wanted to show you a couple of slides which I didn't show you yesterday. You will find the updated slides which I will upload them today to the conference. This is this was what I showed 2 days ago, the power spectrum from the flat, and this is the power temperature spectrum, multiple spectrum, sorry, of the Planck legacy release, which appeared in 2018, and it's the last of the Planck mission. Okay. Nothing really changes compared to previous years. Error bars is slightly smaller, but there are no surprising news. And actually, this is about the polarization spectrum of the PP mode. Is another, we haven't talked about polarization, but there are different types of polarization. This is one which is expected to appear during inflation. There is another one coming from tensor modes, which has not been observed yet, and it will be very interesting to see because it would carry important information about early universe models. And another picture I wanted to show you was about the effect of curvature on cold and hot spots in the CMB, which actually we talked about just on the whiteboard, but this is a visual simulation of how the CMB anisotropies would look like if the universe were open or closed. So in one case, you would see smaller spots of temperature fluctuations and alpha. Now let's move on to inflation. We talked a bit about the kinematics and as well as the dynamics, and we introduced the tower of lower parameters, which are interesting to extract observables, physical observables. And we gave also a couple of examples. And now let's go to this lecture. We'll finish the part about inflation. Let's talk about the big graph, the cosmological some problems. The then dedicates the last part, basically the last hour, to a topic which is supposed to be advanced, so it's not. It's really an off-topic with respect to what I was asked to talk about in these lectures. It's not basic cosmology, but seeing the interest of people during the previous talks, I think it may be the idea to deviate from the program and see what happens when you try to modify the number scale model and to implement some more or less fundamental theory to the cosmological. Okay. With this, so if you're more interested in basic in the basics of cosmology, please consult the textbooks, some textbooks which you will find listed in the slides, or you can also ask. Now, we haven't solved yet the primordial seeds problem, but inflation does that. The primordial seeds problem was basically to answer the question: what's the origin of the temperature fluctuations in the sea? Okay. The answer is given by quantum mechanics. The inflaton, if it exists, an inflaton was a scalar field, and as a scalar field, it's not a classical object, it's a quantum object, which undergoes quantum fluctuations. So these quantum fluctuations, if small enough, could predict perturb the crowd in such a way that directly originates scalar in particular, we promoted a classical field fit to expectation value of a quantum field, which is defined by the background part plus a quantum fluctuation. And for convenience, we write down a scale field, which is the quantum fluctuation times the sum of the background quantity. Remember that for instance, for tensor modes, this f was equal to a. The scale factor for scalar modes, it's well, it is still a scale factor, but then you have to add some term here, some coming from one of the scalar perturbations in the metric. But anyway, this structure is very general, so you can quite illustrative what happens in both the tensor and scalar sectors. And well, one decomposes the quantum field in terms of creation and manipulation operators, coming to space, taking care of the fact that since the field lives on a curve in the background, the vacuum is not unique, so you have to make a choice of vacuum. It's a very interesting chapter in the handbook of inflation. We will not talk about it today, but it's possible to choose a vacuum which reduces to the Minkowski vacuum asymptotically, and the power spectrum, primary spectrum, is the two-point correlation function of the quantum field. Okay. Evaluated at scales much higher than the horizon. Well, one source for these functions u and this function u of k, which are based on Muharrem's society equation, which we already saw in the previous lectures. And one takes this solution at large scale, then evaluates it at the horizon process when the perturbation going with number k crosses the horizon. And this is the definition of your Reynolds effect. So it turns out that according to the inflationary paradigm, the anisotropies of a CME can be explained as originated by partial fluctuations of a quantum field. And if the zero approximation is valid, then these quantum fluctuations are small, and so they have the possibility to reach the required smallness of semi-anisotropies, which remember that they were about 1 part over 10 to the 5. Okay. So cosmology turns out to be an area where particle physics and gravity meet. So it's very interesting. This I couldn't have time to tell you that this means nice to meet you. When we study inflation, we are doing quantum cosmology. Okay, we're not doing quantum gravity, but we're doing quantum physics in cosmology. So the macrocosm, so the biggest, the largest object you can possibly observe, is an actual window of quantum physics. It's a coincidence of opposites. It's amazing. It's very attractive. Maybe that's one of the reasons why I studied cosmology in the first place. And it's here for everybody to observe. Now, what are the inflation spectra then? Now, for a scalar field, the two-point correlation function is on a de Sitter background, so where h is constant, is given by this famous law, which is the square of the Hawking temperature value. And but the actual scalar spectrum is not just the spectrum of delta phi or of a fluctuation, but of the geometry perturbation of constant density hypersurface, zeta, okay, for friends. And that one is turns out to be a spectrum of a field scalar fluctuation divided by the first slow parameter. And since during slow epsilon is small, this quantity may be actually quite large compared to the types of perturbation, which is actually it's simply given by the scalar perturbation. It's the same as scalar perturbation, but normalized Newton's constant. Okay? That's because the gravity polarization modes obey the same Laplace equation of A times delta. From this you can compute so the ratio of the two, the tensor to scalar ratio is 16 times epsilon. So epsilon is smaller. It means that this tensor to scalar ratio is going to be smaller. This is a prediction. We already saw the data, so we already know that this is correct. And the scalar spectral index and tensor spectral index are proportional first order and then is our parameter. So again, we are closer to scaling variance, but not exactly at scaling variance. Epsilon and eta are not identical. So the fact that the inflation predicts a non-scaling variant and almost a scaling variant spectrum is a success. So it's a great success. And furthermore, it also solves some open point we left suspended in the second lecture, which was we assumed that the distribution of multiple coefficients, A, Lm, was Gaussian. And I said, well, okay, fine, let's go with it, but why should it be so? And the reason is that inflation actually does make this prediction. When you perturb Einstein equations and you go to the linear approximation, so you take perturbation which are small. In this case, inflationary fluctuations have a Gaussian probability because of a real imaginary part of that variable u are independent from each other. We have a Gaussian distribution. So actually, also this means that all the point correlation factors, the 3-point correlation factor, 5-point correlation factor, etc., are identically zero. And you can describe the whole statistics just by the power spectrum. And although this is true up to a certain point, because then you have inflation also predicts a small non-Gaussianity. Okay? This is another important chapter of Hamilton inflation, but we won't see it here. So this is the likelihood marginalized, likelihood contour of the plane given by, this is the NS, the scalar spectral index, and this is R, in terms of scalar ratio. And this region is at the 95% of S-level, is a relative region where in this plane. So any model of inflation falling within this region is could be a viable candidate as a model of error unit. Okay, that's risk inflation, which we see later, falls in the best possible spot because it's right in the middle and bottom part. There are other models which are maybe marginally excluded. And actually, many popular models of inflation, early models of inflation, are far away. It's just an example of how that likelihood contour was in 2004. So, with the first year of WMAP data, And this is just forget about these were non-commutative models, so some exotic thing. But this was the, if I remember correctly, this was the quadratic potential. This was quartic, maybe. And 10 years later, with the 2013 release of Planck, this model was already out, and this was marginally acceptable. And other models of exotic or gravity-related realizations of inflation, 2004 were still acceptable, but 10 years later they were excluded. Okay? So this is why nowadays we're talking about precision cosmology. So in the 90s, you would have a rough estimate of everything. In the early 2000s, you started to see some error bars shrinking, and nowadays we are really in the position to exclude a lot of models. So we are doing what physicists are supposed to do. Okay? Now compared to the last release, this goes up to about 0.06. Well, it doesn't look like 0.06, but this plot, yeah, let's say 0.08. So it means that it's about here, so it got a bit smaller, and also narrower. Okay. Good. That's very good news. Now, let me conclude this part of inflation, by saying a few words about how to implement the main quantum field in particle physics. Many of you may have an interest of cosmology, but from the perspective of standard model side. One obvious idea is to identify the photon with the Higgs, because it's a non-scalar we have in the standard model. But this doesn't work because the mass of the Higgs, about 125 GeV, is much smaller than the mass you would require to sustain inflation in an early stage of acceleration. So this idea doesn't work. However, if you couple the Higgs non-minimally to gravity, which means that you have a multiplicative terms between the Ricci curvature and the field, then you do obtain a model which can sustain inflation, but eventually turns out that it's not that good because it has a fine-tuning issue. In this correction of sorry for the typos, I tried to spot all of them, but it keeps correcting from problem. So this model also doesn't work. So you have to add ingredients. For instance, if you add a new field couplings, then you get new Higgs inflation, which may work, but certainly it's not as appealing as the simple idea of identifying a field with the Higgs. But it's a model that is there, and let me look at it if you like. If you like supergravity, you can realize inflation there because we have a lot of boson fields. But in general, you meet with the eta problem, which essentially sums up to the fact that when you compute the eta Slurrow parameter, was here. Well, you can do it, but the potential, the scalar field potential coming from supergravity models in general gives rise to a parameter eta order 1, which is bigger, which means that it spoils Slurrow. So you can solve this issue in several models which have a de Sitter vacuum, and you break the supersymmetry of that vacuum. Crystal alpha transfers in one such model, but there are a few others. So you can embed inflation in supergravity models, but you have to work it out together. Okay? It's not straightforward. There are a lot of local too, but ingredients you have to add more or less by hand. Okay, questions? What was the first question?
About the quickly. It's like how it will allow us to roll out models of and the second is about non-design.
Okay. Euclid in general is expected to give information about dark energy. So I would say that may constrain models of intersection inflation where by the same use the same scalar to describe the different phases of acceleration every and a time. Not sure about other types of models. Regarding non-locality, I simply don't have time to talk about it. Let's say that due to nonlinear interactions of the fluctuation of the scalar field with themselves, can generate a small signal, which basically amounts to a non-zero three-point correction factor, which is called the bispectrum multiple. So inflation does predict a smaller level of locality of order of a slower part. It's order x. So it's very talking about an epsilon order of 1 over 100, and so the level of locality predicted by inflation, primarily locality predicted by inflation, is of the same order. Then you have other types of locality that add up. And eventually you get an effect of order 1. And nowadays the constraints on this it's called the nonlinear parameter. It's basically measures the level of locality more or less. I'm very rough here, but the better part is about order 10. Okay, so it's 0 is still in the error part, but we haven't detected the locality. There are models that predict high levels of locality, which have been already ruled out in many of them. And there are also a few models of exotic inflation, which predict some level observable in the near future. Yep.
Does it have to be
people consider the gate fields, spinor fields, compensates, tensor fields. Yeah, you can do it.
So it's not the reason for it. That's the
It is a simple case. You have many scalars in the supersymmetry, and if you begin supersymmetry, you may be attracted by that. Yeah, you can realize it also with fields with non-zero speed. Or a pseudoscalar, which might actually be the next level going beyond the real scalar. Well, it depends if you have to. I mean, there are models of vector inflation, and of course, they have to take into account a number of problems. And I mean, there is no upper level to the complication or you can insert to your model, so you can do everything if you're willing to make the model as complicated as possible. But there are models of vector inflation that yeah, work, but they're not particularly attractive in terms of simplicity. But in principle, they work. I can give you references about this if you okay, other questions? I sorry, I didn't understand. Library.
Yes.
Wasn't oh okay. That should say something about polarization. Yeah, but yeah, to be honest, I kind of got interested some time ago, and then I moved to radiation wave detectors, and but if I remember correctly, it's one of the missions who progress in the polarization. Well, you have to first define a model which predicts a large enough stochastic ground. We talked about that in the last lecture. Now let's move on to the Big Bang problem, which is actually bigger and better because it creates a singularity problem of GR. So we have Big Bang because according to the standard cosmological model, the universe is expanding, and it's expanding from a point where the scale factor was 0, energy density was infinite, temperature maybe was infinite or was 0, depending on whether you have temperature or not. Anyway, you have zeros and infinities, which means that everything, all of our beautiful picture of the universe stems from a point where the laws of general relativity cease to be valid. So it is quite boring, theoretically, and it's called the Big Bang problem. It can be stated by saying that singular solutions of the Einstein equations are typical. Cosmological solutions, black hole solutions. So that's why we call singularity problem in general. It's not just the Big Bang, it's about the singularities inside black holes. And even if you find one solution which is regular at the t equal to 0, it doesn't mean that the Big Bang problem doesn't exist because you just found one particular solution. But if you look at family of all possible solutions, then you see that it's very typical. However, you can make this argument more rigorous through a series of theorems, singularity theorems, started by the works by Hawking and Penrose in the 1960s. These theorems take various assumptions about the matter content or even the type of dynamics. But recently, Bordeguth and Milenki proved a very simple theorem, which is not based on any specific gravitational dynamics. It can be valid for GR, but supramental theory, defined on continuous time. And also, it doesn't assume anything about the matter content, about the equational state of matter. You will see it in the next slide. So, this is the reason why if you change the dynamics from Einstein gravity to something else, you usually cannot solve the singularity problem. You still find singularities. And one question is also, well, suppose I cannot solve the different problem. Can I live with it? So the question is, what happens at the Big Bang? What happens at the singularity? And it turns out that the physical picture is quite entertaining, and we will see it later. So just a brief sketch of the Corfu2021 theorem. You have an observer in a congress defined by a vector u. You may consider this, imagine that this congress is just a flux of particles and an observer traveling through these particles. Using a covariant formalism, so without specifying any background, can define a generalized Hubble expansion. Here I put very just to complete this, but it's I won't go through that. And you define an average expansion as the integral over this parameter sigma, which parameterizes the your word line from some initial to some final point. So the VGB theorem states that if this average expansion is a positive definite, it's called the average expansion condition, for almost any time-like non-geodesics, so the observer would or could not travel at the speed of light, then your space-time is geodesically fixed. Means that the length of the proper or affine, proper or affine length of geodesics is finite. The proof is given in one line because if the average expansion condition is true, then this average expansion is just a constant divided by the length of your geodesics, which is finite. What does it mean? It means that here you don't have to assume inflation. You assume that your universe, in average, expanded. It also means that it could have been through phases of refraction. Not too many, but in average, your universe expanded. You're not assuming homogeneity, isotropy, no. Okay. It's very powerful. It looks like the final word about the ratio stating that yes, you do have a cosmological singularity. However, this is not quite correct because all of these theorems, Cosmology theorems or geodesic theorems, reach the conclusion that the geodesics are incomplete in the past. But it doesn't mean that the visa defines a global singularity of the space-time. To do that, you would have to show that it happens for all of the observers at the same time. Okay. So maybe there are models actually that evades the VGB theorem. So you can construct counter proofs to the counter examples. But it is still quite general and quite common. So, and it's much simpler to prove than all previous theorems, and that's why I like to teach these lectures and to encourage students to look at the original paper, and because I think it's a beautiful and powerful result. All right. So let's assume that we cannot get rid of the Big Bang, and we must live with it. So what would we see if we went through a singularity or towards the singularity? Well, it happens something quite surprising, that in several models, mainly in GR with different types of assumptions, but even if you modify gravity or if you change the number of space-time dimensions, generally you find this result, which is that spatial points decouple and space-time becomes homogeneous at every point near the singularity. So if you go towards the singularity, space-time becomes homogeneous. Been shown in many cases, and that's so if you assume that it's valid for as a law, then you put it in conjecture, which was made by Minsky, Kalakov, Lifshitz in the late 60s, early 70s. Which means that you can use some homogeneous background on some time-dependent background to describe this symmetric near this space-time near singularity. How does it look like? Well, space-time becomes homogeneous but not isotropic. It means that you can different directions can behave differently. So if you take different scale factors at the different directions, you are in the realm of Bianchi-9 models. So you have basically three independent scale factors, in 1, in 2, and 3, which are all the functions only of time. And well, you can parameterize the scale factors in different ways. If you parameterize them as power laws, then the coefficients of the power law have leaving this potential, which means that during the evolution towards the singularity, you will bounce back and forth along the walls of this potential. This model is called cosmological linear. Means that this factor at each direction changes behavior in a chaotic way. Doesn't mean a random way, chaotic way. During the evolution backwards in time, so going towards the singularity. Okay. In fact, the BKL singularity can be understood in this case, in this sense, if you parameterize the scale factors as terms of a number of defaults. What you find is that when you go towards the singularity, so towards the right, one scale factor always decreases, but the other two always oscillate. So you always have two scale factors that decrease towards the singularity, but one that increases. It's like if the universe were closed, where a ball of a ball, then this ball would change its shape when shrinking, because when it shrinks in two directions, but it expands in one direction. And this infinitely many times going towards the singularity, because at some point this Kastner error ends. It's called Kastner Kastner solution, and two of the scale factors change evolution. So instead of decreasing, the decreasing one starts to increase, and vice versa, and so on and so forth, infinitely many times. This is a very big singularity. So you reach a singularity with infinitely many possibilities. There are other models of singularity, for example, which come from supergravity. You can study the same problem supergravity as well. And some models even reach the point of describing the shape of the singularity. They're quite interesting, but we don't have time to talk about. And okay, all this applies to the Big Bang singularity. But again, the fact that we have a singularity also in astrophysical objects such as black holes, which nowadays we have good evidence that they exist. But you understand why many theoreticians are trying to tackle this issue of singularities, because the theory of GR works incredibly well, but unfortunately there are these points where the theory itself breaks down. Questions? Well, they are the three things. So it's if you think about the closed universe, that's the radius of the universe along one direction. So as I said, the geometric picture is that of a ball that squeezes in an oscillatory way as it frees. So it's size of the universe along that direction. This is an anisotropic universe. It's homogeneous but anisotropic. So there is no. Well, no, because you can interchange the directions if you want, but the directions are not equivalent. I mean, they are different. It's an isotropic. So you don't have it's not conformally equivalent to moving cost, like in a homogeneous pair, like a trigonometric over one on the ground with only one step back.
So which is a conclusion, the Big Bang problem.
Yeah, the singularity, the Big Bang exists in GR and in many other modifications of gravity. Inflation, the other conclusion is that inflation doesn't help to solve the problem because you have a singularity when you have inflation. Cyclic models are supposed to not solve the problem because they fall within the scope of the BGP theorem. Because for many cyclic universes, the average expansion condition holds. Another conclusion is that the Big Bang singularity has this structure. So if you approach it, you will see this decayal behavior, which is chaotic. It's described by chaos theory. And that's pretty much the conclusion. I mean, it's not written in stone because, as I said, there are the theorems based on the lexicon completeness fall a bit short of proving that there is a global singularity, but the evidence shows that the problem should be considered seriously. Okay.
This behavior singularity is an example or general
it is general. I mean, if you change the ingredients of your theory, like instead of GR you take something else, or instead of 4 dimensions you take 10, you may have different types of structures. Some cases even non-coordinates, but it's quite generic because this conjecture holds it's called a conjecture because it's based on a number of complete examples. Okay, so there is no theorem, but there are a number of examples, and they all point in this direction. So it's quite generic. Well, maybe it depends on the model. Many of those claims were made up before this theorem, and
like the ones using offline computation.
yeah, but yes, but when we are talking about quantum gravity, that's another part of that. Now I'm talking about VR and IMO also in supergravity. Well, it can be based on a Bianchi model, Bianchi nano. No, not a Bianchi model. Then let's move on. The cosmological constant problem is much harder than the Big Bang problem. Why? Because we don't observe a Big Bang, but we do observe a cosmological constant. So maybe if you're more empirical than a theoretician, then you may not care at all about the Big Bang. But you do care about the cosmological constant because we do observe something like that. Okay? And it's also harder because there are many solutions to the Big Bang problem, which are model dependent. There are many more solutions to the cosmological constant problem, but nobody is happy about that. Well, not everybody is happy about that, okay? Because the proposers are quite happy about their solution. Anyway, what is the cosmological constant problem? We can state it in different ways. The traditional one is maybe also called the old cosmological constant problem. First, let's state what the problem is. And the problem is that the energy density of the dark energy component, so dark energy constitutes about 3/4 of the content of the universe, but it's not dense. In fact, it's the least dense of them all, because if you compute its energy density, it's about 124 orders of magnitude smaller than the Planck energy density. So the question is why this hierarchy of extremely small numbers. So it's the problem is perceived as the fact that we find an extremely tremendous fine-tuning between the energy densities of your okay. And it looks like it's a constant, cosmological constant, because its equation of state is, as far as we know to date, is compatible with the cosmological constant with the equation of state. Why is it a problem? The problem can be stated in terms of the quantum field theory. So we know that quantum field theory works, so the standard model works. So we may try to interpret the cosmological constant as the contribution of the fields of the standard model in their well, but this doesn't work. Let me first say something else. If the problem is not the smallness of itself, but the fact that you cannot explain its smallness with known physics. For instance, at equality, so when the matter and radiation energy density were the same, the energy density was about 10 to the minus 113 Planck energy. It's very small. It's actually comparable with the energy density today. Well, it's 10 orders of magnitude bigger, but well, okay, we are 10 to the minus 113. Is that a problem? No, because you can calculate this from particle physics, and you get the correct result. Even the thermal conditions of the universe at that time. Okay. Or you cannot do the same for the energy density of dark energy today. So this is the code of the old cosmological constant problem. And there is another description which was made of a new cosmological constant problem. Why is it of the same order of magnitude of the matter energy density? someone feel that this is a problem. To me, it's not, but okay, along with it. And then there is also the coincidence problem, stating that, well, since lambda started to dominate a very small redshift, why is it so? Why so recently? But to be honest, I never understood the point here, because if you look in terms of proper time, we find out that dark energy started to dominate when the units was about half its speed. Okay. So in terms of a redshift, yeah, we see some coincidence, some fine tuning, but in terms of a proper time, so maybe someone more expert than me on this point could make a better argument about the coincidence problem, but anyway, this is how it is. Now let's see the old cosmological constant problem, which, as I said, is the fact that theory cannot explain the smallness of lambda. If you compute the vacuum energy density at the tree level using the electroweak sector, we see that this is an order of Higgs mass, where GF is the Fermi coupling, and this is about 10 to the 56 orders of magnitude bigger than what you observe. Okay. And you can say, okay, this is a level estimate. Let's be more refined and let's go to one loop. And so you calculate your bubble diameter contribution to this integral. And if you do a simple cutoff calculation, you find that the result is order of, well, the fourth power of your cutoff. But if you take the Planck mass as your cutoff, then you find that the famous 10 to the 124 or 10 to the 120, depending on whether you take very distant mass or not. This is a very famous number, 10 to the 120. It's not correct, or let's say it's not the best result we can get, because cutoff regularization breaks Lorentz invariance. So it may be better to use dynamic regularization. And if you do that, you end up with an estimate, more refined estimate, which when you plug all of the species of excuse me, of the standard model inside, you get that you're off by 10 to the 56. So the same order of magnitude as the 11. So it's not as big as the often quoted the 10 to the 120, but it's still a huge, it's still a huge height. Okay. If you get the two loops, things get worse. So going to higher loops doesn't help. Now, but with numbers, I'd like to give you an analogy which comes from genetics. So suppose you want to ask yourself, so what's the chance, what's the probability that one person has a specific phase? Okay, the answer is given by genetics. This is another question about the phenotype of the person. But you can shift slightly to asking what's the chance that a certain person has a certain genotype. So genetics says, well, each individual's genome has about 3,350 loci in heterozygosis, which means that it can produce 2 with 3,350 different gametes, which corresponds to 10 to the 1,000. 10 to the 1,000, okay? It's a tremendous number, super huge. But its explanation is extremely simple once you know what's the origin of the face of the person. So the cosmological constant problem exists because we still don't know what's the genome of the universe. So we don't know what the genetics means in the case of the universe. Okay. You can find much bigger numbers in nature, which has a perfectly clear explanation. So to summarize, the standard model doesn't predict the correct value of the cosmological constant. Some people may say, well, but I don't expect the standard model to be valid on a curved space-time. Maybe other explanations. Yes, maybe. You still like the quantum theory, you can have supersymmetry, but then you have to break supersymmetry, and it's very complicated. It's not impossible to do it, but it's very complicated. And plus, there is another way to state the cosmological constant problem, which was noticed by Heiberg in 1989. Actually, it was a review of the cosmological constant problem, but giving some new ideas. Is the fact that GR behaves in a quite strange from the point of view of field theory. When you are on Minkowski, you can shift your method Lagrange by a constant, and this will not change your equations of motion, which are the gradient of energy moment potential equal to 0. However, as soon as you switch on gravity, you no longer have this symmetry, because when you shift the Lagrange, so you shift the energy momentum tensor, and the Einstein equations are not invariant because you are shifting the value of lambda. Okay, you're changing the value of lambda. This is weird from the point of view of field theory because in general, in field theory, Latin solutions are symmetric with respect to some subgroup of your symmetry group without the need of fine-tuning your parameters. So in the case of gravity, the symmetry group is big. It includes diffeomorphism. The vacuum solution, Minkowski, carries invariance under the Poincare group, but when lambda is different from 0, you no longer have a way to continuously connect this vacuum solution with solutions with no trigger. Okay, so it's another way to state that you cannot apply all the concepts of the theory to GR in a straightforward way when lambda is constant. There is yet another way to state the cosmological constant problem, which may come with 4-pi puzzle. Was noted by Manavan. And 4-pi puzzle is the following: that the duration of the era when matter and or radiation were dominating, so before the onset of late time acceleration. So the duration of that era can be computed in terms of b-foldings, and it is exactly equal to 4p. Yeah, you can change your definition of number of foldings, but the argument doesn't change. You get a specific number up to 1 part over 1,000. Why should that be so? It's really, it looks like a joke, but it's based just on the history of the universe, on the onset of the dark energy era. It depends on the reheating because it depends on when the radiation domination era starts. But these uncertainties are order 1 actually here, so you don't get you don't deviate much from this approach. Okay. There are different ways to state the cosmological constant.
But it's very sensitive to the value of lambda.
Yeah, but this is observed.
Yeah, but if you change rho lambda to a different value, perhaps you don't change too much.
But but here you do the change I mean, here the point is just using the observations. Okay. So the only thing you don't know really is your heating temperature.
I mean, not kind of one different value of lambda, the number.
Yeah, but you would change it, but you would still have a large higher. If you change it to the point of reducing the hierarchy, then you would also change this number. I mean, you have enough fine-tuning to make sure that this number will not change unless you really reduce the fine-tuning to something natural or acceptable depending on your perception. Okay, so what did people try to solve? It's already 1 hour. Let me finish with this and then I will take a break. Questions and break. Simple ideas. Yeah, many that unfortunately not work. Simplest is okay. Since the scalar field worked for early viewers, why not using another one for daytime users? It's called quintessence. Its problems are that you have to choose an out potential, not motivated by anything but observations, and you have fine-tuning on initial conditions. Okay, this is a problem. So sorry about that. It's very attractive, but it doesn't work. Then you may say, okay, let's modify gravity and think that what is driving acceleration is the geometry itself and not some other component. You do that, but on one hand, you don't know how to motivate your final model. There are models of XAFR, but there are many others. More sophisticated modification of gravity. So you end up with a Lagrangian, which is can work, but you don't know where it comes from. Basically, by hand. And many models have actually some moderate, not a big one, but still a bit of it. Okay, so maybe they are not the ideal solutions. Then another proposal was that well, the cosmological principle is okay, but we know that we have clusters of galaxies surrounding large volume regions, and maybe if instead of assuming an effect of background, you take into account the fact that signals propagate through these large voids, then you may explain acceleration as a spurious effect of the fact that you're using a lambda CDM. Okay. Yeah, this is also quite attractive because it doesn't add new physics. It just makes more sophisticated use of known physics. However, first models were in tension with data, or they included fine-tuning, and later models removed the fine-tuning, but at the price of making these models much more complicated. And there are proposals. For instance, if the quintessence field is no minimal coupled with other matter, then you do get acceleration without fine-tuning, where I'm not sure where this idea has been elaborated too much. Or you can also think of data acceleration as a manifestation of some condensate in the universe of different types. Okay. Before taking a break, do you have questions about the lambda problem?
That we can extract the languages from Cosmology. And we will contact all the functions of the language. And we can just sort of about these new explain about that. We can even use that
it's the Hordesky theory, unitary and renormalizable as a quantitative theory of electrolytic strong interactions
So
and
the
gravity.
theoretical motivation is say move the with the rate of GR.
Yeah, if you want, yes. At some point, you will have to embed your at least from my perspective, you will have to embed your model into theory. Otherwise, you're just doing model building. You can invoke symmetries. You can constrain the shape of your Lagrangian, but eventually you end up, you start and you end up with the model, not the high energy physics.
But GR is not
Huh?
GR is not high intensity theory.
Yeah. Well, GR is not an effective theory.
And we don't want to do theory and just want to resolve the problem of Latina.
Well, but maybe some people do want to look into quantum gravity because a model building can work up to some point. Then you may ask yourself, what's I think we are asking different questions here. From a point of view of F of R per se, you do end up with in a talk Lagrangian, which actually has the unit powers of a scalar to the power of some integer number, fifth data, but it's
But that part is the
yeah, for the SK, yeah, you can find other Cambridge models which actually also give interesting imprint, for instance, on luminosity distance of gravitational waves, and people are considering for the SK actually host models which are a step beyond on the SK. But from my point of view, it's just the 3.0 version of F(r) in the sense that yes, you modify the dynamics of your gravity and metric fields, but you eventually fail to embed these models into some bigger picture. So one may say, okay, yes, your model works, but how does it fit with quantum field theory or with grand unification? Maybe you're not interested in those questions, okay? But that's totally fine. In fact, many people don't believe that there exists a cosmological cosmic problem. But since society is also made of opinions, my opinion as a lecturer is that it is a problem and I want to solve it with the theory. Okay, are there other questions? Yes. It's the way you couple your context scalar with matter, for instance, with dark matter, so that modifies the dynamics. So, for instance, in your Langmuir equation, you have a source term with a dark matter element. Not right in your top. Yes. 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 I'm thinking we're still going to model. When you modify gravity, you modify the coupling between gravity matter, matter detectors between detectors and gravity, and you complicate the model. It's like a fixing equation. Just that minimally coupled Higgs doesn't work. So you make it minimally coupled to gravity. Fine, but then you still have some problems when you have the more ingredient. I call it Frankenstein complex. If it doesn't work, you can't consume and get something else that works. Fine, but it's happening. Again, yeah, you can do everything, but then how do you embed your model into some coherent description of gravity and quantum matter? That's another issue. Back to there are models circles of emergent gravity, where gravity you don't quantize gravity. You just think that gravity is a larger scale manifestation of some other degrees of freedom, some effective description, and they partially solve the quantum constant problem. Partially means that they reach the point where yes, the quantum constant is smaller because there is a discussion mechanism, but then they don't really explain why you observe this specific part. Actually, they don't prevent gravity, but you embed gravity into some coherent description. And I think what your comment is related to this comment, but yes, you can find models where everything is self-consistent. But my opinion is that when you go beyond self-consistency, then there is a lot more things. Okay, so I think it's a good time to take a break.
Yeah. Can you remember to type the attendance link? Okay, so there are people that.
Okay, although we are later, like since we are later, I propose to merge the tutorial session with the lecture, because the tutorial session was meant to be a space for debates or questions. But since we already asked questions during the lectures, and possibly also at the end, we just go through and so we will just finish on schedule. Okay. All right. So this is the last part of the lectures, and probably it's going to be the one which will create more debate, something of which we've seen already now, which is cosmological models coming from quantum gravity. So one may ask, okay, so what does quantum gravity predict about cosmological observations? Can it fare better than ad hoc models? So these are legitimate questions, and today we'll try to describe, to give a partial view of the state of the art. So the ideal proposal of quantum gravity would be a theoretically rigorous theory with good properties like no infinities in the ultraviolet, good low energy on the cubital limits, so that you recover GR or also the standard model if you like. It should be testable, because if it's not testable, then you're hard to do physics. And in particular, it should ideally solve the Big Bang problem, the cosmological constant problem. It should embed inflation in some way or another. And the point is also falsifiable, because it could fit all data, but we might want also some new prediction, which could be tested with cosmological observations, astrophysical observations, tabletop experiments, whatever. Okay. We're far from the ideal, but let me first make a warning remark about vector method of calculations. This is something that also Renato mentioned in her lectures. We think about quantum gravity as a perturbative in theory of some sort or another. We say, yeah, well, forget about this ideal picture. You're not going to get anything. Why? Well, because quantum gravity effects are expected to be important at the high curvature or short distances. And from the point of view of cosmology, these cubical corrections, how do you build them? You only have two scales, the Planck length and the Hubble parameter. So all your corrections will be powers of N Planck times h. And if you measure it today with you plug h naught here, and you get some effect which is order 10 to the minus 60, possibly exponentiated to some power. So no way that you will observe any quantum gravity stuff in cosmology. Whether this is just an argument based on considering quantum gravity as something like higher order cubical corrections that allow to access gravity. But you can do very, very different things from that. There are no perturbative effects. For instance, just a trivial example, if you add a third scale of your model, larger than the Planck scale, imagine that you have some quantum states of geometry which with this characteristic scale much larger than Planck. Then the combination of all possible quantum corrections also includes L, this capital L, to some powers which sum up to 0, and not all of these corrections are answerable. So the main message in this slide is that don't trust the back of envelope arguments against quantum gravity. Just do the calculations. You can do them on a bigger envelope, and if they look interesting, just take your notebook and go through it, because you may find interesting surprises. Okay. Now, inflation. There are many models of quantum gravity or inspired by quantum gravity which embed inflation. I give you just two classes of examples. One is from loop quantum gravity. The cosmological realization of loop quantum gravity is called the loop quantum cosmology. To date, there are at least 3 different versions of loop quantum cosmology, depending on how you treat cosmological perturbations. One of these is based on inverse volume and Coulombic corrections, which I will not discuss now, but basically what to do here is to consider an inflaton field living in a geometry with dynamics dictated by well, the basic ingredients of the quantum factor. Dynamics modifies the dynamics of the inflaton, and eventually it modifies also the power spectrum, the semi-spectrum, and this is the low multiple spectrum. This is a standard GR, and these are different spectra depending on how you tune some parameter of the model. And remember, 2 days ago, I said, okay, beware of the cosmic variance. If something that is from GR, don't immediately claim that you have a suppression or enhancement of a spectrum. In this case, you have an enhancement, but you have to take a larger value for the parameter because of, and only here, which is a very, it's basically the first point of a SMB multiple data. In these all these models, you just assume that you have an inflaton in this modified background. You don't really explain why you have an inflaton. And in fact, loop quantum gravity does not even aim to integrate the standard model within itself, although there are also proposals towards that direction. So this type of models may be unsatisfactory for different reasons, in the sense that you introduce a quantum gravity ingredients, but you find a model which is consistent with observations. You find also some new feature, but it's not really the end of the story. It's not maybe not even the beginning, because you're not explaining why you have an inflaton and why this inflaton is low rolling. Or there are also papers that address that issue in terms of the probability of inflation. This is just a sketch. Okay. The idea here is that inflation, even if the energy scale of inflation is much smaller than, sorry, the curvature, the inflation is much smaller than Planck energy, you can still get the macroscopic effects because your semi-spectrum gets modified. And loop quantum cosmology is not a real example. String theory, you have very different realizations of string inflation. It depends on how you compactify your n-dimensional space. In this case, the inflaton is a degree of freedom which naturally comes from the theory. So it is, in this sense, it fares better than loop quantum gravity, because here the inflaton is already there, if you wish. There are many, however, there are many ways to have an early universe stage of acceleration. And this is a table of some of them. They are all in agreement with observations. They give different predictions for instance, the tensor modes. For some, the tensor acceleration is basically zero, it's unobservable ever. Just forget about it. Some other models are more promising because they produce a larger R, and some produce actually a relatively large level of non-Gaussianity, so that you may even hope to get some Gaussian signal. And the fine-tuning is relatively mild, it depends on the model. In some cases there is a lot of fine-tuning, in ours it's very, very mild, it's acceptable. Yeah? Which model here do not relate to others? This one is not a model of inflation. All the others are, and in all the other cases, you do not have to add the scalar field. It's already there because you may think about it as a radian. So basically, an extra direction which is described by a scalar field, where is the distance between the two branes which collide. In the case of a chaotic universe. Or in other cases, it's a modulus field. It's basically a scalar field coming from your supersymmetry potentials after you compactify your extra dimensions into Calabi-Yau space. And in this case, the pattern is one of the models. So basically, the first 2, 4, 6, the pattern is already there because it comes from the way you compactify your theory and how the fields, the gauge fields, for instance, behave on this compactification. The case for? No, as I said, in that case, you assume that the matter content of the universe is a scalar field. As I said, it's a very introduced wave pattern by hand, and you work out the predictions, but you don't have the scalar field for free. Or I say for free, but you really have to do a lot of work to build this model. But they come from string theory. There are many ingredients to work with. Some people may find this model too complicated. Others actually, as a proof that the string theory can give observable predictions. Anyway, this is a list. Now let's go to the given problem. But how does quantum gravity fare with respect to the given problem? Not better. But with caveats. For instance, canonical loop quantum cosmology, which Renata talked about in her lecture. You have a probabilistic interpretation of lambda. We will see now what it means. In loop quantum gravity, well, to loop quantum cosmology, the Big Bang is replaced by a bounce. We'll also see what it means. Spin forms, you basically confirm the same results of loop quantum gravity. Spin forms, if you wish, is a partial integral presentation of loop quantum gravity. And group field theory contains the model. So group field theory is supposed to be the mother theory of spin forms and loop quantum gravity, which is also quite interesting. In string theory, you can resolve singularities by T-duality or by other means. For instance, if you consider that the theory is intrinsically non-local, also in the low energy limit you have the local operators, these local operators of sphere singularities. There are other examples like the COSM model, I will show on a slide. Causal dynamical triangulation, which is another theory field. As far as I know, the problem has not been tackled. In local quantum gravity, which is a perturbative field theory of gravity with local fundamental non-local operators, which is unitary, normalizable, or even finite in some realizations. And then, as I said, local operators, just like in string theory, smear singularities into something finite space-time, so you replace the Big Bang with bounds. Although, in the case of black hole singularities, this is not straightforward. You do not resolve singularities through non-locality, but through conformance. And then there is another class of models, multi-factor spacetimes, which I've been working in recent years. The variant spacetime becomes fuzzy, the short scales, and no longer makes sense to talk about singularities at all. But these are not yet embedded in a full theory of quantum gravity. In the case of asymptotic safety, the problem has not been tackled yet, as far as I know, nor in causal sets or in unimodular differential gravity. Examples: canonical quantum cosmology, Wheeler-DeWitt equation. It turns out that the wave function of a universe is 0 at the Big Bang, which means that the probability that the Big Bang happens is 0. That's how you dispense with the problem in this case. In the case of loop quantum cosmology, you don't say that the probability of the Big Bang is hitting the Big Bang is 0, just skip on the Big Bang. The loop quantum cosmology, the evolution of the universe is goes on the discrete steps. This is not an assumption; it's a result of the theory. And it turns out that basically the Big Bang at A equal to 0 is not in this discrete set of steps. So basically, you go through the Big Bang. You skip it. I think it's the honest way to state what happens. And then you go through it, and in terms of a continuum evolution, like when you approximate to a continuum, you can show that your Friedmann equations display bounds, finite bounds with a finite energy density, which is about roughly half the Planck energy density. And then you go through and you find a phase of contraction, so you have this bouncing scenario, which already, however, has been questioned by also some components of the quantum cosmology itself, because it was relied on several assumptions. Then there are other models, like the comfort model, where it comes from supergravity, from n-dimensional supergravity, and when you reach a singularity in the limit of a Newton constant going to infinity, all of the dynamics of the field, everything reduces to the dynamics of the knowledge density of a particle in a percent okay, this instead of space-time gives way to a purely algebraic structure. This is something mind-boggling, but I wanted to mention it just to show you the diversity of solutions that people propose in different models of gravity. Now, the multiple constants. This is interesting. In theory, proposes the landscape as a solution. There are several models where let me do it. interaction. There are several models which haven't said anything about the cosmological constant problem, field theory, no local quantum gravity. Well, in this case, with time, so I should update this reference, but there is one multifractional theory can explain the dark energy just as a geometric effect. We still a lot of work to do about it. Also, causal dynamic triangulations, as far as I know, didn't tackle the problem. In canonical quantum cosmology, there is a probabilistic interpretation. In local quantum gravity, well, people didn't really care, but there are a few proposals, isolated proposals. Couple percent give some strange prediction about lambda and also symptomatic safety. They have to predict the number. It's amazing. But under several samples. Then there is Patmanav's emergent modular gravity to solve the vector pi puzzle in such a way that Patmanava could explain why lambda is small, but he could explain why lambda takes a part. Yeah.
You said like it's much more big.
Yeah. Maybe. Yeah. Yeah. In fact, here I'm not selling quantum gravity as a solution for the problems. And just stating what the status of quantum gravity with respect to cosmological problems.
But is there any way to actually
you interpret lambda as the expectation value of a fermionic condensate whose degrees of freedom come from the gravitational connection calculated on the genetic method. But there is a lot of assumptions, so it's not a complete it's a possibility, but it should be worked out. The message here, the implicit message is that the typical thing, is the cosmological constant problem a unique or an infrared problem? And we say, well, it really depends on the solution. And you may think about it as an infrared problem because clearly it has to do with the large scale properties of the universe. But its origin could be in the UV, like the QFT attempt to solve the cosmological constant problem is a UV attempt. Okay, it doesn't work, but it could have worked in a different form. So the difference between UV and infrared in the case of the cosmological constant problem, I think, relies more in the answer than in the question itself. Okay, canonical quantum cosmology, we lead with equation. One can find that depending on whether you take the Vilecki or Hartle-Hawking wave function, you get a different probabilities, and they all are exponential, but with a crucial minus sign difference. And in the case of a Hartle-Hawking wave function, universes with a small lambda are favored, so this probability is high. But clearly, you can re-normalize your wave function with a constant term which depends on lambda, and you totally erase this effect. So you cannot really use these probabilities at face value. And in the case of the other canonical quantum theory, which is loop quantum gravity, this is what I mentioned before. There are some attempts to explain a lambda from SU2Q spin network. So where they basically the building blocks of your state of geometry are not spin networks but fat spin networks, because the learning produces so fatness of the spin network. And you have to do a lot of things, but eventually you end up with reformulating the dynamics of space-time in terms of the Dirac equation. And if this effective spinorial degrees of freedom condense, then you only need a fat tuning of 1 part over 100 to explain the law. Yeah.
What do you exactly mean by inflation? Like 2 phases or?
Did I talk about inflation? I mean here.
Yes.
It's basically it refers to the fact that you expect you have you want to calculate the probability to start with the universe in a receiver phase. Okay. And you can do it in a framework of really with the cosmology. And depending on your assumptions, you may end up with different types of results, depending on the factor. Typical RB19 or Harper-Hawking. But basically, it's the question is what the probability that the receiver being started with the receiver phase. Yeah, I would think so. But again, you can start with basically just results. But you can, I think it's a model dependent question. We see it on the same framework, you can do it in different ways. So different that you get the opposite is right now. Proof theory. What is it? Do you know? Does anyone of you know or heard about proof theory? Yeah, it's quite fascinating. It's defined as a theory of fields living on a group manifold. So instead of living on a manifold described by coordinates, you live on a group of manifold described by group elements. You can do perturbative QFT with such an object, and a lot of it have to do with the space-time or with PR. Good question. It's still open question. But it turns out that on one hand, this way of describing degrees of freedom on groups include the results found in spin forms and loop quantum gravity. And it turns out that the cosmology, which was sort of assumed that loop quantum gravity, is actually a natural byproduct of this theory. So from this theory, you can directly get cosmology with a very reasonable assumption. Instead of like truncating symmetries, as you do in quantum cosmology, here you get it from the full field. This is extremely fascinating. And if you're more fascinating, I think that you can do this with much less effort than getting local quantum cosmology from quantum gravity. In fact, you can play with the quanta of proof theory, and if there is a quantum condenser, then the condensates eventually give rise to a homogeneous and isotropic continuous spacetime. And furthermore, you can also get some prediction about the cosmological constant, because in this case, the wave function of a universe of canonical quantum cosmology is, well, its role is played by the expectation value of the group field And in this case, it goes as 1 square root of lambda. So again, you have, if you want, the preference of smaller values of lambda, without having all that normalizability problem of canonical cosmology, because here you are in a Lagrangian theory, so you don't have the ambiguities as the Hamiltonian formalism. Again, this is just the beginning of the resolution of the problem, just what is known so far about the problem. It's okay, small values are preferred. This is not a prediction of actual value, so but I leave it here for your curiosity. String theory. String theory has about 10,500 vacuum, just to state a number. So the question is, how many of them can produce the universe we live in? Notice that this number is much smaller than the number of possible configurations from genetics, which was at 1,000. So when people get scared about this number, string theory, then we will look at take this example from biology. You won't get scared anymore. So here, genetics is a string theory, and it turns out that you have enough vacua satisfying well within the satisfying observations. And how you select them? Well, either by statistical selection, which means basically that they are many enough that you just see that the problem is just a statistical thing, so you have just enough realizations, so trouble about that. Or by anthropic selection. Yeah, there are many versions of the anthropic principle, but even if one uses Weinberg's strictest anthropic principle, you get a resolution of the problem. However, now it's in question whether stable de Sitter breakouts are so common in string theory, which gave rise to all of this landscape literature, but I won't talk about it. This is another realization, quite clever realization of a statistical or probabilistic resolution of a topological constant problem, which shouldn't be dismissed so lightly. But again, it has its problems. Does not sense. Well, here, let me just skip. I just put the slides, but I don't want to go through the content. Here, you don't have space-time. You have a discrete structure of partially ordered points, which, when sprinkled over on some embedding, reproduce the causal structure of continuous geometries. It happens that the cosmological constant arises as the action of some of these fundamental elements, and you can make a rough calculation of the energy density of this contribution, and with many assumptions, you end up with a very modest tuning of your parameter or the one, and that will be actually the correct value. But then it doesn't work for various reasons. First of all, you don't really embed this prediction into the theory itself. You really have to make a huge number of assumptions. Fine tuning is hidden in the model because the same numbers give you well, are in contradiction with the CMB data. So in order to respect to see the CMB fluctuations, this parameter alpha, which is the number of fundamental elements, is instead of order 1 is order 10⁻⁵. The dynamics of this theory is unknown, largely unknown. So I'm not even an expert on causal sets, so I'm not the best person to present these results. But just bear in mind that there is a theory which is not even based on Riemannian geometry, which made this brave attempt into cosmology, which is quite isolated because we don't really have a cosmology of causal sets yet. But people are making progress, and eventually, but hopefully, they will revise or refine this argument. In the case of synthetic safety, one is quantizing the theory, the functional normalization group approach. And if you quantize just GR, you have only two couplings, Newton's constant and lambda. And you realize asymptotic safety. And if you plot your trajectory on a lambda G plane, I don't know if you can see it very well, but it turns out that spend a long normalization group time near small values of T. And you kind of have an effective description of cosmology by promoting these two couplings to time-dependent variables, where the time dependence comes from the fact that these couplings depend on the cutoff, and you have to make a cutoff identification. So the old cosmological custom problem is reformulated by asking why is the perturbative semiclassical regime of a normalization group trajectory fine-tuned is so much? There is no answer to that. However, there exist also trajectories with lambda equal to 0. So it's not impossible to realize a small lambda in asymptotic safety. And if you take this effective description in your practical cosmological equations, you find some effective time-dependent contribution to dark energy and eventually some number, but it's all these things rely on many assumptions. By the way, in my opinion, maybe not in the opinion of many people working on asymptotic safety, is to look at through the perspective, different perspective, which is one of the sound quantum gravity approach, which is a quantum field theory where you can do perturbative calculations. It is asymptotically safe. So in this sense, it belongs to the same class of theory. But here, the perturbative QFT approach is used, but not the traditional one. But instead, you take a sub approach, which means that you replace all your three-level propagators with a fully resound propagator. Okay, it's a conventional quantum field theory. But if you do that, you can calculate in the vacuum expectation value of contribution of things to behaviors, and end up with a correct result. It's the correct number. However, here, theorists of quantum field theory may object that you're not doing QFT because you're taking, for example, propagator. But I find the results so intriguing that I would at least know that it exists and give something. Questions so far? In this case, yes, because thanks to us proxy. Yeah. So you are asking if there are bouncing models in quantum gravity?
No, I'm asking about the minimum for you, like for the bounce.
In the case of loop quantum cosmology? Yeah, in that case, the minimal volume is it's a Warner Planck. It's larger than the Planck volume. The energy density, there, for instance, is about half the Planck energy density. So it's order of Planck, but slightly big. Well, in cosmological setting, what do you mean? How do you interpret time? Well, there is no meaning if you go to a singularity, but if you go to a bounce, there is a meaning to before. It's just like what happened before yesterday. I can see what happened before yesterday because yesterday nothing singular happened. So it just you can your geodesics go through t equal to 0, which go to negative times, but the time itself is a parameter. It doesn't matter whether it's positive or negative. Well, the entropy in that case, I think people well, it depends on the type of perturbations you have. But in general, I would say that because even in the case of quantum cosmology, you can consider adiabatic or isotropic perturbations. But I would say that in general, you but the problem of entropy in bouncing models depends on whether you have cycles. And in this case, you don't have cycles. You have only one. Sorry, give me 1 second. Number 2. Sorry for the interruption. We were talking, yeah, about entropy in IPG. don't remember really what people said about it, but I think in the first papers they showed that I mean, it didn't give rise to any new problems. So all the basic post-Big Bang features of standard inflation were covered. Yes.
We look at cosmology, where there is a balance. And then isn't it essentially like a target expansion? Because the unit isn't space-time accelerating when there is a balance, and then the expansion, and then the shrinking.
That's true for all bounces. So whenever you have a bouncer, you have super acceleration. Super acceleration means that the first zero parameter is negative, which means that your Hubble parameter is decreasing. Sorry, it's increasing. It's basically a way to state that it's accelerating more than in ordinary inflation.
So we cannot address the issue that inflation addresses.
No, because you have to explain how to generate scalar perturbations. So if you don't have matter, you have no scalar perturbations. You have to have some. Also because a solution in vacuum is not the same as solution with matter. So if you have scalar field, then that's the solution of your Hubble problem, your Miller-David equation. But if you don't, then you spoil it. No, because at some point the scalar field will cease to be in a slower phase. It will decay into matter through reheating, and then you will have radiation domination and matter domination, and ions will expand without acceleration. So you need to add an extra component because the super acceleration near the bounce is near the bounce. Then that's yes, no, it's no problem. What about? Yeah. Well, in this case, you don't have a singularity. So BGB singularity is a description of a space-time when you do have a singularity. Well, the simplest description is based on the Yankee models, just in your definition because the scale factor by definition. Where the scale factor is scale factors are given by constant solution. Our law, so which is a singularity. So zero, imagine is the degenerate. You don't have a degenerate. More questions? Okay, move on. We are with time. It's bounded from above. So let's try to respect that. So let's move from these problems of a Big Bang and the lambda problem and move to other observations. We saw that some theories of lambda GR can embed inflation or can realize inflation, which is good. Are there other features, like what happens to gravitational waves? This was a question asked on the first day, right? Well, in principle, one that's a take this back. Say, well, yeah, the frequency of gravitational waves is too small. How we observe gravitational waves in the daytime universe where the frequency is small, so well, there is no chance that we observe anything about quantum gravity gravitational waves. Then it happens that it's not that straightforward. There are basically two ways to check theories beyond Einstein. Here I'm not talking about quantum gravity per se, just even quantified gravity, because anything beyond Einstein can be tested through two mechanisms. One is through the production of gravitational waves. So at the moment where the gravitational wave is produced by a physical system, for instance, or primordially fluctuation. And for instance, if you modify the black hole solutions, if you take a different type of gravity where you don't have the Kerr black hole solution but something different, this will reflect into the waveform of a gravitational wave. Or in the case of primordial gravitational waves, if you find a blue tilted tensor spectrum, then you may get an exotic stochastic background in this case. The other sector to look for modifications to GR is in the propagation of gravitational. So once the gravitational wave has been formed, it will propagate through space and time and will reach us. So here you can consider modified dispersion relations. That's very classical thing to do. More complicated is to check that the phase in the waveform well, it will carry, despite the amplitude, it will carry some modifications, phase and the amplitude. Luminosity distance could have some, could receive effects from modifying gravity or the dynamics. And again, if you look at the primordial waves, the stochastic gravitational wave background is generated also through the propagation of the primordial spectrum of waves through the universe. So here the question is, okay, in general, I will, if I modify my dynamics or my geometry, I will get some effects. The question is whether quantum gravity can give visible effects. For instance, we know that if we take the host or Kondensky, we can get big modifications to the luminosity distance, which can be tested by LISA. This is one result that we published a couple of years ago. But let's say if you want is an infrared modification of gravity. So you may ask what happens to something that is supposed to be some UV modification of gravity. Okay, let's see, for instance, the spectral relations. You break your length invariance in general with frequency and the momentum will not be linearly proportional. You can add some higher order power of a moving momentum, and if you take this phenomenological modified spectral relation into account, then you can calculate the group velocity of your wave, and by considering the difference between this group velocity and the speed of light, you can find an expression for this fundamental mass capital M as a function of the frequency of the gravitational wave and some inverse power of the difference between the velocity of the gravitational wave and the speed of light. So when you modify the dispersion relation of gravitational wave, it will no longer travel at the speed of light, and this modification may have an observable impact. In fact, taking the first gravitational wave event found by LIGO, the LIGO-LIGO collaboration, and plugging in the numbers, its frequency corresponds to very, very low energies, and it gives rise actually to a very tight constraint of the velocity, propagation velocity. So if you take n equal to 2 here, so you have basically a particle modification on your right hand side. Here you are in the realm of models where you can recover the entropy RLO of black holes if you modify your dispersion relation. So not quantum gravity, these are phenomenological models. Okay? If you do that, you'll find a lower amount for n, which is useless because it's 10 to the minus 3 electron volts, so it doesn't say anything about high energy physics. Then there are other model-independent arguments in quantum gravity, also from string theory, which suggest that n is equal to 1. So here we have a cubic modification. In this case, the lower bound for n improves, but not much. So basically, you cannot use these results to test to constrain your fundamental mass scale of your theory of quantum gravity, if any.
The value is not obtained with respect to the counterpart field, because we have a counterpart and electromagnetic counterpart in this case. But this is obtained from the
yeah. So basically, yeah. Yeah, here this is not a standard size. So in fact, from this you can get a bound of the mass of the graviton. You can take assume a standard dispersion relation, but graviton mass. I say graviton interchangeably as gravitational wave, but for me graviton here is a classical. But yeah, as you said, you don't need an optical counterpart. So one may reverse the question and say, okay, suppose that m is large, like at least a order of the LHC scale. So what is n, the range of n, which will be compatible with the observations of LIGO Virgo? The answer is no integer, so n is between 0 and 0.76. And in fact, it has a geometrical interpretation in some theories of geometries with a multifractal structure, where n is related to the Hausdorff dimension of spacetime. The Hausdorff dimension is how volumes scale with the radial size. Okay? And I mentioned this example because in quantum gravity in general, spacetime, when you reach a continuum limit, when you can talk about spacetime, in general doesn't have a multi-scale structure. Multi-scale means that the properties of geometry change with the proto scale. Sometimes it's a multifractal, sometimes you cannot talk about the fractals. All people in general say fractal, but it's like abuse of terminology. So for instance, if you have a model with a Hausdorff dimension equal to 2 in the UV, then n should be 0.5, and this means that modified dispersion relation of that type will be compatible with observations if m is greater than 10 to the 17 GeV, so very close to the Planck scale. Of course, these arguments are valid for theories which break Lorentz invariance, because this breaks Lorentz invariance. But yeah, this is another story. So when we ask, okay, are there theories which break Lorentz invariance this way? Yes, in this class of multifractional spacetimes, but for instance, these are not not work as a models of quantum gravity for other reasons. So they're not engineering normalizable at the same time. It's not you can do phenomenology, but it's very hard to move to the computer. And in the first set of lectures, I mentioned that in PR, the amplitude of the gravitational wave, talking about astrophysical gravitational wave, is inversely proportional to the luminosity distance of the optical counterpart. Here we're talking about standard science. So in general, I define the gravitational wave luminosity distance as the inverse of the amplitude. And when you deviate from PR, this ratio, digital over DEM, be equal to 1. So if you modify the dynamics of the gravitational waves through the kinetic term, for instance, you end up with a phenomenological expression, which is a with time, so we have 1 plus some correction, which depends on the scale which you find in your modified. Yes? The spectrum itself is different. This is the point. Now, what happens here is that you take a lens in the kinetic term, and which tells you that what is basically the dimensionality of your gravitational wave, we call it capital gamma, which will depend on the absolute dimension of space-time, which depends on this measure, and also on how this kinetic term scales with the momentum. Okay, I haven't still said where do these modifications come from. I am just for a moment. I'm just making an exercise. If you do this exercise, you find that the amplitude no longer goes as 1 over d, but as a d to this power of gamma. So this is ends up with this type of formula where this small gamma is a capital gamma, but I change notation just because here I use it as a phenomenological formula whereon I can place observation constraints. Now, let's stick with phenomenology so far. So I'm saying that I modify the measure of the action, and I modify the kinetic term in a quite general parameterization, and I find this expression where small gamma is basically this capital gamma. It's the dimensionality, the scaling of a gravitational wave at scales N star, where N star is actually hidden here. Here you can imagine, for instance, take this as a modified kinetic term. Now it's Lorentz invariant with a higher power of k, and in front of the higher powers of k, you have a vector scalar N star. So you have this scalar from these phenomenological modifications, and you ask, can I detect this modification from experiments? The answer is yes. If even when this scale is ordered the Planck scale, if this parameter gamma is slightly bigger than 1. I haven't said anything about that. This is a phenomenological parameter. It can be anything in the real field. Okay, not talking. I haven't said that yet about quantum gravity. I'm talking about phenomenology. I make this modification of my quadratic action for the gravitational wave, and obtain this result for the ratio of luminosity distance for some standard size. So I don't have the results, but basically we tested this with a mock-up with the binary neutron star observed the standard siren observed by the LIGO-LIGO collaboration plus theory, and also with a supermassive black hole simulated from this attack. If we did that, and we found that this correction could be above the uncertainty, experimental uncertainty of the luminosity distance for LISA if a gamma were slightly larger. So yes, we can get modification, but what theories do predict such a result? Now, from a geometrical perspective, these modifications, this is a typical plots of capital gamma, which would arise if my space-time geometry would change through a change in the measure and or a change in the kinetic term. And to get an observable result, I would need to reach the GR result gamma equal to 1 from above, not from below. Only from above, I will be able to get a sizable effect in luminosity. So, we took theories of quantum gravity, which predicted a modification in one or both of these terms, and we classified them. It's a long table, and it turned out that there were only 3 theories where gamma could go to 1 from above. Where 2 of them, one a model, it's not even theory of quantum gravity, a model called by Padmanabhan, and another model based on commutative geometry predicted a correct deviation here in mesoscopic scales of more than 1 to 120, the famous number of the back of the envelope. And here the back of the envelope is right. You cannot really get any observable effect. Gamma is closer to 1 to get an observable effect. Remember that here we have gamma minus 1. However, in the case of loop quantum gravity, spin from group theory, kinematical states of geometry do give rise to a profile of gamma like this, where the deviation can be in principle large enough to give an observable effect. Problem here is that we don't know if this bump is an artifact, a numerical artifact of this result. So these results are numerical. You cannot solve this exactly up to numerics to find the geometry associated with certain quantum states, and these are kinematical quantum states and not even dynamical quantum states. So we don't know if this is an artifact of the results known so far, or it's that. Anyway, there are not many possibilities, but the models of quantum gravity, theories of quantum gravity we know, could give rise to an observable signal in the luminosity distance. So yes, the back of the envelope argument was right. Here it's a way to prove it. Okay, and we haven't even given a definitive negative answer for all the nodes. So let me conclude with the gravitational stochastic background. Remember this plot where I showed the stochastic background from inflation, which is quite flat, while below the sensitivity curves of present or future experiments. So to get a detectable signal, we do need some mechanism blue tilting the primordial spectrum so at higher frequencies the amplitude of a spectrum would cross the sensitivity curves. For example, Starobinsky inflation, tensor to scalar ratio is order factor -3, it's very close to 0, and this is the result. So you will never realize a Bluetooth spectrum in standards or single simulation. This is Starobinsky inflation. We talked a lot about it, but I should have shown this slide at the beginning, but well, I decided to put it at the end. It's based on the assumption that you modify GR by a quadratic term. If you transform from this Jordan frame to the Einstein frame, you can recast it as a standard GR plus a scalar field, where the scalar field has this specific form. And it's an excellent agreement with observation because this is where it lies. And sorry, it's not very visible, but the scalar spectral index is 0.967. This is exactly what we see. And as I said before, the tensor to scalar ratio is ordered 10 to the -3. This model is not embedded in a theory of quantum gravity because no FOR model can come from a quantum theory. The reason being that in a quantum field theory, you will always generate terms which depend on each tensor. However, well, this is the best phenomenological model we have, but it doesn't produce any observable stochastic spectrum because it is red-tilted, so NS is smaller than 1. Okay, let me skip a bit of the spectral shape. So the question is, are there models motivated by quantum gravity give rise to blue-tilted primordial spectrum? And question number 2 is, does this primordial tilted blue spectrum give rise to an observable stochastic background? And after going through the literature, to find 5 models, none of which is well, except this one, because it's embedded in a theory of quantum gravity. So let's start with no longer Starobinsky inflation. This is the generic action of no local quantum gravity, which I mentioned before. It is a higher order in the kilometer terms, and it also has no local operators. These no local operators help to make the theory unitary and improve also the normalizability of the theory itself. It turns out that if you choose the form factors of these functions of the inversion carefully, you can get a unitary and normalizable theory. Actually, you can find it. And you can also embed the Starobinsky inflation in this theory. Okay? So you have to tailor, but regionally tailor your form factors. You can embed no longer Starobinsky inflation. So this theory already gives all the nice predictions of Starobinsky inflation. But the problem is, and you need to have correction from the no local factors. So the problem is, however, that no matter which form factor you choose among those allowed by the theory, or at least about most used in the theory, it's true that it gives rise to blue-tilted spectrum at the same scales. So the primordial spectrum is blue-tilted, but it never really gets that boost towards higher amplitudes at high frequencies. And so eventually it always leads back to the Starobinsky, local Starobinsky plateau. So the main message here is that a blue tilt that you see in this case does not guarantee that you have a detectable signal at higher frequencies. Look, for instance, here you have a very big tilt, but actually very low amplitude. So when it reaches these frequencies, it's not enough. Okay. So a blue tilted primordial spectrum does not guarantee a blue tilted stochastic background at the high frequencies. Okay? So this model doesn't work. So it doesn't give an observable prediction as far as the stochastic background is concerned. This is a model where inflation is realized on an commutative background. It's a cosmological model, it's not embedded. Quantum gravity is motivated by string theory. So if you wish, it is a phenomenological. And it turns out that it gives rise to a blue tilted and also blue tilted stochastic background, which barely crosses the cycle sensitivity curve, while respecting all the bounds like C. So yes, gives rise to can give rise to an observable signal, but this signal will be weak and only observed by one experiment, which is still under approval. And also this model is phenomenological. It's not embedded in a full zero graph. Motivated by. But that's the best we could find. Okay, these 5 models were the best we could find in but for space times, again, it depends strongly on the running of the tensor index, which is actually, it is negligible always at the CB scale, but at the diesel frequencies, the running is important, so you must take it into account. And that's why I put it in the slide in our lecture, because I was customarily ignored for when doing inflationary physics. When you do the stochastic background, you cannot longer do that. Okay? Even if it's very, very small at the same scale, doesn't matter, because here the range of frequencies spanned by this plot is huge. Again, it crosses the cycle sensitivity curve, but this model in particular is not embeddable in a multifractional zero quantum graph. String gas cosmology, in this case, you have a gas of strings in the universe in a thermal equilibrium. You don't have scalars, you don't have inflation. You can explain the CB fluctuations as thermal fluctuations of this gas of strings. So this is an alternative to inflation. It is motivated by string theory, but it relies on assumptions. It's not fully embedded. So again, it's a model, it's only theory. And this one has a better chance, apparently, if you do a calculation, but then you realize that if you take into account some approximations you made on your power spectrum, this result cannot be correct, because there is a maximum amplitude defined from a full expression. So again, you expect the signal to be to reaching here the bottom of the cycle curve. Nothing better. Finally, new periodic scenario where instead of inflation, so if inflation is replaced by 2 breaks which collide. This is a new periodic. Maybe you're familiar with the periodic scenario, which predicts unacceptable perturbation spectra. This one respects all the bounds of the CMB, no problem, because you have the S-brain in your spectrum. And it also can predict a blue tilt, which can actually cross even the Einstein sensitivity. Here you have to be careful, because if any spectrum that goes too sharply up, it may hit the Big Bang synthesis bound. So here you have to take into account reheating, which in general bends down the spectrum. plus or minus above. So whenever you have reheating your early universe model, this in principle can help you to avoid this bound, which goes to all the frequencies, so you cannot you must avoid it at some point. But again, it depends on the reheating temperature. So it may be even better too early to reach the sensitivity curve, or well, this is a possibility. And among these models, it's the only one that hits the Einstein telescope. Doesn't hit LISA, probably. And again, there are several assumptions on this model, so you can still debate whether this is how quantum gravity is this model. But again, here what we did was just to ask the questions of what our present knowledge in quantum gravity models, quantum gravity models, can say about Mr. Calcagni. So I feel you have a lot of questions more, but to answer all of them, we need your help. So join our community if you're interested in this issue. And thank you very much. Are you talking about immunological distance or Mr. Calcagni? Ah. Look, people in the 90s were wondering whether it would ever be possible to discriminate between different models. Nowadays we can. So, apart from that, which is a heavyweight argument, I would say in the case of immunological distance, the effect coming from deep host models is of a different type because it has a specific relative dependence. Yeah, suppose, yeah, but what I mean is that, for instance, the redshift dependence of a ratio doesn't change depending on the model, and in that case, how do you know which model best represents your data? Then we can try Bayesian selection. So, for instance, calculating the information tree of all of the models that can fit your experimental curve, and see which one has the lowest information. Actually, we did that with mock data with different modified gravity models, not even modified gravity models, and yeah, you can in principle you can make this Bayesian selection, where you can do better. Certainly, you can always do better. At this stage, we're not given. Well, we care about the degeneracy, but at this stage, I think it's much more urgent to see what the theories on the market can predict. And as you can see, they cannot predict much. This is from the side of quantum gravity. We have a better exception of velocity distance, which we don't know if it's theoretically robust, because we don't know some details of the quantum state. For the stochastic background, I showed you a few models, but none of them really comes straightforward from full theory, and there are uncertainties of these models. So we are at step -1, not even step 0. We are trying to build a catalog of prediction from theory. But then we are, on the other hand, in parallel, we are thinking about the generacy, at least for modified gravity models, because they are actually easier to manipulate. And we are doing it, well, in my case, Lisa, but other experiments are thinking about these issues. But in general, I would say that there may be tools to discriminate between different models. Because they can all fit the data, but then, well, I think Bayesian selection is quite the powerful way, and it's starting point. It's not particularly easy, but mathematically you can do it by yourself on your laptop. Yeah. No, I mean, you can generate polarization with a perfectly classical fields as soon as you produce some pseudo fields, some character in your action. It can come from matter, come from gravity itself. Yeah, but I mean, lambda CDM is not only fits the data, but a lot of data, okay? And that's what the spirit in which we should test our modified gravity or gravity models. We shouldn't focus only on one set, on data set, but on all possible things. Yeah, automator is good. If we also would observe polarization, then we would expect that the same modification of gravity or the theory in general matter giving rise to polarization would also explain other observations. And I think also the spirit of multi-message astronomy is precisely to use many sources to converge to the coherent set of predictions. It's a difficult task for any model or theory, because we have to look for everything. So rotational curves of galaxies. I haven't talked about the dark matter, but I would expect that I mean, you can have a dark matter in a theory of quantum gravity, but if you could have a theory of quantum gravity that could also explain dark matter, it would be even greater. But maybe here I am asking too much. But since we don't know what the final answer, then we can make all possible. The important thing is that at some point we have to make the best of what we have. And since I think we are beyond the stage of asking, is there a theory of quantum gravity? I think there are many theories of quantum gravity, too many. So let's start to do phenomenology with what we have, as rigorously as we can. At least this is how I reacted to my I think that 20 years from now, all of what is said in this last hour will become obsolete. I don't think anything will be safe. it would be strongly model dependent. I don't think there is an a priori answer to that. About the sorry, I cannot hear you with the mask.
There is one way to look at those but using that.
Okay, yeah, well, as I said, there are many ways of look into modifying the area in reproduction and propagation radiation waves. I'm not very familiar with those results, but I mean there are many proposals which focus more on the physics near black hole system, which I haven't mentioned, and not because I don't like them, but just for lack of time. But there is, for instance, a review by Yagi Pretorius, Nunes Yagi Pretorius, about modifications of the waveform for propagation radiation waves. And the list is huge. I mean, they include modified gravity models, continuity models. There is a lot of work going on, and for instance, if you look at the manifesto of the fundamental physics working group of PISA, there is a list of this. Probably, I think also the details of results are mentioned there. By the way, we are, of course, beyond the lecture time. We are already in the tutoring plus discussion time, so if you have questions about the previous lecture or more general questions, other people can answer and it's open later. Yeah, well, to be honest, I started to work on dark matter only in the last few months. So I declare myself quite ignorant about the issue. As far as I know, the greatest, the great majority of proposals to address the dark matter problem are of particle physics nature, so no quantum gravity. There are models of modified gravity that try to explain both dark matter and dark energy, and they are more or less lucky about that. And we'll go back to maybe some interactions about the cosmological problem. I have been trying to embed to explain the quotation cubes with one of these models with living in a multifractal space-times, but they're still working on that, so I don't want to say anything about the results. In some cases you cannot explain, in some cases you can. Again, well, the particle that matter is attractive because you make use of standard QFT with exotic physics, which is not exotic matter, but it's a physics that we understand. We don't have to modify the concept of space-time in a strange ways. I would say that any solution to the dark matter problem should be able to explain all the data, not only the rotation curves, but also the bullet cluster, gravitational lensing, which is displaying line sharing, dark matter search, and so on and so forth. Plus, so the side from particle that dark matter, I would say there are only partial results. I mean, for me, it's taking weeks to get the rotation curves, and I haven't talked about even gravitational lensing. So you know, I think that's a huge chapter by itself. Yeah, well, yes, large scale structure, of course. It's, fortunately, we have so many data, cosmological data, that we have to any serious answer to these problems should address more than one data set. Yeah.
We are only to look quantum gravity, and it can show some
Yeah, I think I saw that some time ago. So it's practically recent. But yeah, as a matter, you can.
allow us to make a difference
When you modify the waveform, you have a better chance because the waveform is such a complex object to observe that I mean, you have a pattern of features there, okay? So if your model predicts a certain pattern and if that pattern adjusts to data, then it will be great. So different models will predict in general different pattern, maybe in the oscillation amplitude or position. So some amplitude of the phase will change in different ways, so you can discriminate different topics. However, having said that, so far the waveforms are reconstructed from LIGO camera data are all quite compatible with GR. Actually, it's one of the greatest recent successes of generation. It's very hard to calculate the waveform even in GR. So this is a big challenge of future experiments to deal with the waveforms, and especially when you modify the standard paradigm, because it's a very complicated topic, even in standard GR. So, but yeah, it's certainly one of the most promising fields where to look for to break in the generacies or to look for observers.
So I think we can be here, so let's try to go to the